Hello everyone, today we will be going over the USACO bronze problem, fair photography.
Alright, so let's take a look at the problem. The problem states that Farmer John's N cows, where N is at most 100,000, are standing at various positions along a long one-dimensional fence. The ith cow is standing at position xi, an integer in the range 0 to 1 billion, and has breed bi, either G or H. No two cows occupy the same position. Farmer John wants to take a photo of a contiguous interval of cows for the county fair, but we want all of his breeds to be fairly represented in the photo. Therefore, he wants to ensure that for whatever breeds are present in the photo, there is an equal number of each breed. For example, a photo of all Holsteins is okay, a photo with 27 Holsteins and 27 Guernseys is okay, but a photo with 10 Holsteins and 9 Guernseys is not okay. So we need to help Farmer John take his fair photo by finding the maximum size of a photo that satisfies Farmer John's constraints. The size of a photo is a difference between the maximum and minimum positions in the cows in that photo. It is possible that Farmer John could end up taking a photo of just one cow, in which case this photo would have size 0. So let's look at a test case.
So here we have our sample input. We have our Guernseys denoted in yellow and our Holsteins denoted in pink. So as you can see, we have a number line with all the cows and their positions that we got from here. Just by trying some possibilities out, we get our optimal range has length 7. But we need to do this without trial and error. So since we're trying to find a window, a natural first instinct would be 2 pointers, right? What I did initially was I let 1 represent that a cow exists at that location, created 2 arrays for G and H cows, took a prefix sum over both, and had 2 pointers. And the way I move these pointers is that if the difference was equal, then I would move the right pointer right to make a bigger window, else I would move the left pointer right to shrink the window and try to make the range valid. But this didn't work. Pause the video and see if you can figure out why. The reason this didn't work is monotony. So definition of monotonic is a function that moves in one direction. Here, this would mean that there's just one fixed left endpoint for every right endpoint that would make the window switch from invalid to valid. You'll see this used in binary search problems a lot too. But back to this problem. We know that that's not true. So now what do we do? My next approach was to treat it like an optimization problem. I let G equals 1 and H equal -1, and we wanted to find the longest subarray that sums to 0. To further optimize, we use hashmaps to store the earliest index each prefix sum has occurred. So when a sum repeats, we know instantly the longest window we have so far without rescanning. But we're missing one thing though. What if they're all the same breed? The hashmap only tracks subarrays that are fair when there are both G's and H's. If an array has just G's or just H's, it's automatically fair. But our hashmap doesn't count that, so we need to count this separately after the earlier approach completes. And we're done. So let's look at the implementation.
So let's go over the implementation. We begin by reading an input using the Kattio class, which I have implemented here and I'll link in the description. So then we proceed to encode G as -1 and H as +1. And just quick note, either sign works. What matters is they're opposites, since a fair window is one where these cancel to 0. Then, since cows aren't given in position order, we need to sort indices by position in order for our fair picture to be valid. So I like to do this by creating an integer array because custom comparators do not work with primitive types. So we need to have it be integer instead of int. And then I sort using a comparator. Then we have the hash map, where I will store the earliest position where a certain running prefix sum occurred. So we need this because a subarray sums to 0 exactly when the two prefix sums are equal. So storing the earliest occurrence lets us grab the longest possible zero-sum window. And since we grab this the instant a sum repeats, this is O of 1 lookup instead of rescanning. So that's a great optimization to keep in mind. If this sum has occurred before, then everything between that earlier point and here has an equal count of G and H, meaning it's a valid fair photo. And then we're going to record the earliest left boundary for this prefix sum so future occurrences can reference back to it. Only the first occurrence matters, since it gives us the longest possible window later. So that's the whole reason why we need the hash map, so that we keep track of the first occurrence where a prefix sum occurs, so that we can get the longest window that will cancel out that prefix sum, essentially. But then we have one case that the hash map doesn't see, because the hash map's focusing on trying to neutralize it. But if we have just G's or just H's, our sum will all be positive or all be negative. So that's not going to work with our hash map, so we just need to count this one manually. And then we print out our answer. So that's the implementation. Let's test this one out. So here I have my file uploaded and we are going to submit. And we're accepted. Yay!
So what are some key takeaways? Well, for starters, the two-pointer technique requires you to check if your condition is monotonic. Otherwise, the two-pointer technique will not work. Additionally, maintaining balance between two counters is a very useful technique when identifying the longest interval. And finally, always check for single category cases separately. That's all for now. Thanks for watching.